June 1941. An obsolete tank is about to be sunk in a London lake. Not for scrap, as an experiment. A Hungarian engineer has convinced British generals that tanks can swim. No giant floats, no special boats, just a canvas curtain. Everyone thought he was crazy, until the tank started floating. 3 years later, this crazy trick would save D-Day. Thousands of soldiers landed alive thanks to a concept everyone rejected. This is the story of Nicholas Straussler, the man who taught tanks to swim. Stay with me. Nicholas Peter Sorel Straussler was born on May 7, 1891, in Budapest, Hungary, when the country was still part of the Austro-Hungarian Empire. His family wasn't wealthy. They weren't politically connected, but Nicholas had something money can't buy, a mind obsessed with solving impossible mechanical problems. In 1910 or 1911, at just 19 or 20 years old, Nicholas left Hungary and moved to the United Kingdom. The exact reason is unclear. Perhaps opportunity, perhaps adventure, perhaps simply a young man searching for where his talents would be valued. What we do know is that he arrived with almost nothing but boundless ambition. In January 1911, at the age of 20, Nicholas filed his first British patent, a rotary internal combustion engine. For an immigrant with no resources or connections, to file a patent so early demonstrated not only technical skill, but also extraordinary confidence. The engine was never mass-produced, but the patent established Nicholas as a serious engineer. During World War I, Nicholas likely worked in one of the hundreds of armaments factories supporting the British war effort. His knowledge grew, his reputation as a problem solver spread. He had a knack for looking at conventional designs and asking, why don't we do it differently? After the war, Nicholas remained in the United Kingdom. In 1923, he married Edith Arbib. In February 1933, he became a British citizen. But his Hungarian identity never completely disappeared. He maintained connections with Hungary. He visited regularly. He sold designs to Hungarian companies. He was a man caught between two worlds, British by adoption, Hungarian by birth. Between 1928 and 1933, Nicholas ran a company called Folding Boats and Structures Limited. The name was exactly what it sounded like, folding boats and collapsible structures. Nicholas patented several flotation devices, including versions that could be folded for economical transportation. This obsession with buoyancy was no accident. Nicholas saw a fundamental problem: how to move heavy equipment across water. Bridges could be destroyed. Rivers and canals were natural obstacles. Any modern army needed to cross water quickly. But how? Boats were obvious. But slow, floating bridges were useful. But vulnerable. Nicholas thought differently. What if the vehicles themselves could float? In the 1930s, Nicholas worked with several British companies, Alvis Cars, Vickers Armstrong, and others. He designed armored cars, light tanks, innovative suspension systems. Each project bore the Straussler signature: clever, unconventional, often more complicated than necessary. His fellow engineers considered him brilliant but difficult. Nicholas had strong opinions and didn't compromise easily. His solutions were technically elegant but sometimes impractical. He was the kind of engineer who prioritized elegance over simplicity. But there was one quality that defined Nicholas above all else: persistence. When he encountered a problem that fascinated him, he didn't give up. He returned repeatedly from different angles until he found a solution. And the problem that would fascinate him more than any other was this: how to make a tank float. In 1940, with Europe in flames and Britain fighting for survival, this seemingly eccentric obsession would become critical to the Allied victory. Tanks are heavy, incredibly heavy. A medium tank from World War II weighed 30 or 40 tons. Some weighed 50 or 60 tons. Solid metal covered with steel armor. The physics are brutal, dense objects sink. To float, an object must displace a volume of water equal to or greater than its own weight. A tank is the exact opposite. Lots of weight, little volume. It's designed to be compact and dense. Making a tank float defies basic physics. Engineers had been trying to solve this problem since World War I. In November 1918, just as the war was ending, the British tested a floating version of the Mark 9 tank. It was huge, clumsy, impractical. It was never produced. During the interwar period, several nations experimented with amphibious tanks. The Soviets developed the T-37, a light tank with thin armor that could float, but it was too vulnerable for actual combat. The Japanese developed the Type 2 Kami and Type 3 Kachi, which used disposable floating pontoons. It worked, but the pontoons were massive and difficult to transport. The British experimented with the AT-1, an experimental tank large enough to float unaided. But it was so massive that the design was completely impractical. There was no way to transport it efficiently or produce it in useful numbers. The fundamental problem remained. Combat-useful tanks were too heavy to float. Tanks light enough to float were combat useless. It seemed like a fundamental impasse in physics and engineering. Nicholas Straussler didn't accept this. He'd worked with flotation devices for years. He knew the answer wasn't to make the tank lighter. That compromised protection and firepower. The answer was to add temporary flotation. In 1934, Nicholas abandoned his previous approach of collapsible external floats. They were too bulky. Each float was roughly the size of the tank itself. Transporting enough floats for an entire tank unit was logistically impossible. Nicholas approached the problem from a completely new angle. What if, instead of rigid floats next to the tank, there was a flexible curtain around it? A screen that created volume when raised, but collapsed to almost nothing when lowered. The idea was radical, almost absurd. A canvas curtain would transform a 30-ton metal tank into a boat? Most engineers would laugh at the suggestion. Water-resistant fabric? Canvas supporting 30 tons. But Nicholas didn't think conventionally. He saw the mathematics. If the curtain were tall enough and sealed properly, it would create volume. Volume would displace water. Displaced water would generate buoyancy. The physics would work. Of course, there were 1,000 practical problems. How to seal the tank's base against water. How to keep the curtain rigid against waves. How to propel the tank through the water. How to do all this so that it could be quickly removed when the tank reached the beach. But Nicholas loved practical problems. They were what got him up in the morning. He had a conceptual solution. Now he just needed to prove it worked. Nicholas presented his floating curtain idea to Vickers Armstrong, one of Britain's largest military equipment manufacturers. They were skeptical, very skeptical. Imagine the meeting. Nicholas excitedly explaining how canvas could make tanks swim. Experienced engineers exchanged glances. Someone probably mentioned that canvas tears, that waves knocked down fabric, that the whole idea was ridiculous, but Vickers had a policy. Test ideas before rejecting them outright. So they gave Nicholas limited resources to build a prototype. If it worked, great. If it failed, at least they would know for sure. Nicholas worked for months refining the design. The curtain would be made of treated waterproof canvas. It would be attached to a horizontal steel platform welded to the tank's hull. The curtain would be supported by horizontal metal hoops and vertical rubber tubes, inflated with compressed air. The inflation system was critical. Nicholas designed compressed air bottles and pipes that would quickly inflate the rubber tubes, giving the curtain rigidity. In theory, the screen could be erected in about 15 minutes. When the tank reached the beach, the crew would quickly collapse the curtain. Initial British War Office tests with Nicholas prototypes showed that a light tank, propelled by an outboard engine, swam reasonably well. But there were problems. The curtain was delicate. Waves caused instability. The system seemed workable in theory, but fragile in practice. In 1941, Nicholas finally received a real tank for experimentation, a Tetrarch, a British light tank that was being withdrawn from active service. The Tetrarch was small and militarily obsolete, but perfect for testing. Nicholas equipped the Tetrarch with its buoyancy screen. But there was another critical problem: propulsion. how to make the tank move through the water. Nicholas's solution was ingenious. Instead of breaking down the tank to obtain engine power for the propellers, he used the tank's rear pulley. A gear ring was attached to the pulley, and the corresponding pinion gear drove the propeller. Thus, the movement of the tank's tracks itself drove two propellers approximately 28 inches in diameter. The propellers were designed to rotate around a vertical pivot for steering and to raise around a horizontal axis to move out of the way. When the tank reached land, it was an elegantly mechanical system. The first test took place in June 1941 at Brent Reservoir, also known as Hendon Reservoir, in North London. Among the spectators was General Alan Brooke, Commander-in-Chief, Home Forces. If Brooke wasn't impressed, the project would have died there. Nicholas must have been nervous. Years of work depended on the next few minutes. The Tetrarch was lowered into the water. The curtain was raised. The propellers began to turn, and it worked. The tank floated. It moved through the water. It maintained stability. General Brooke was impressed enough to order additional tests. Nicholas had proven the concept. But proving a concept and producing combat systems are very different things. Discouraged by the success of the Tetrarch trials, the British Army ordered the development of a production version based on a different tank, the Valentine. The Valentine was a British medium infantry tank. It weighed approximately 17 tons, significantly heavier than the 7-ton Tetrarch. Making a Valentine float would be a true test of Nicholas's system. The Valentine DD duplex drive, named for its two propulsion systems, tracks on land, propellers in water, prototype began testing on May 21, 1942. Initial tests were promising. The tank floated. It moved through water, but then disaster struck. During a subsequent test, possibly involving machine gun fire to test the curtain's vulnerability, the Valentine DD sank. We don't know exactly what happened. Perhaps the curtain was punctured. Perhaps the seal failed. Perhaps waves submerged the curtain. Whatever the cause, it was a serious setback. But the concept still seemed sound enough that in June 1942, the Ministry of Supply authorized the manufacture of 450 Valentine DDs for crew training. The decision was pragmatic. Even if the Valentine DD never saw combat, it could train crews in amphibious operations. The DD system would be produced, refined through real-world use, and eventually adapted for better tanks, and it soon became clear which tank it would be, the American M4 Sherman. In April 1943, the DD screen was adapted for the Sherman. The Sherman had several advantages over the Valentine. It was newer, it had better armor, it had superior firepower, and most importantly, it was being produced in massive numbers by the Americans. If the DD system could work on the Sherman, thousands of amphibious tanks could be available. This would fundamentally change amphibious operations planning. Modifications to the Sherman included sealing the lower hull against water, adding propeller drive, adding Straussler's floating screen around the hull with inflation system, and training crews in special procedures. The base of the canvas curtain was attached to a horizontal, boat-shaped platform made of lightweight steel welded to the tank hull. The canvas was supported by horizontal metal hoops and 36 vertical rubber tubes. A system of compressed air cylinders and pipes inflated the rubber tubes to give the curtain rigidity. The screen could be erected in about 15 minutes and quickly collapsed when the tank reached the beach. In practice, there was approximately 3 feet, 0.91 meters, of freeboard above the water. In combat, the flotation system was considered disposable. It was assumed that crews would remove and discard it as soon as conditions permitted. In practice, some units retained the flotation equipment, and their tanks were used in several amphibious operations. The Sherman DD was ready, but ready for what? Where would it be used? The answer would come in secret planning meetings for the largest amphibious operation in history. In 1943, the Allies were planning the invasion of Nazi-occupied France, Operation Overlord, which would culminate in D-Day. The challenge was monumental. The Normandy beaches would be defended by concrete bunkers, pillboxes, underwater obstacles, mines, and tens of thousands of German soldiers. The first Allied soldiers to land would face devastating fire. Traditionally, amphibious invasions relied on naval and aerial bombardment to suppress defenses before landing. But everyone knew that bombardment wouldn't destroy all defenses. Soldiers would still land under intense fire, and here was the critical problem. Heavy tanks couldn't land with the first wave. They had to wait for beach engineers to establish landing areas. This meant infantry would land without tank support, vulnerable to German machine guns and anti-tank fire. It was General Percy Hobart, commander of the British 79th Armoured Division, who saw the potential of DD tanks to solve this problem. If tanks could swim from the transport ship to the beach, they would arrive with the first wave of infantry. They would provide immediate suppressive fire against German positions. Hobart was known for embracing unconventional technologies. Its 79th Armoured Division developed a variety of specialized tanks, nicknamed Hobart's Funnies, flamethrower tanks, carpeted tanks for crossing sandy areas, mine-exploding tanks with rotating chains, and of course, amphibious DD tanks. Planning to use DD tanks on D-Day began in 1943. Extensive testing was conducted in sea conditions to verify that the tanks could operate in real waves of the English Channel, not just on calm lakes. Tests showed that the DD system worked, but it had serious limitations. The tank only had about 3 feet of freeboard. Waves 4 feet or larger could submerge the curtain and sink the tank. This meant that sea conditions on D-Day would be critical. Furthermore, DD tanks were slow in the water, only a few miles per hour. They couldn't be launched too far from the beach. The ideal distance was between 1,000 and 2,000 yards offshore. Any further, and they would take too long, leaving them vulnerable to German fire and sea conditions. Crews had to be extensively trained. Operating a DD tank in the water required completely different skills than operating on land, navigating, dealing with waves. Knowing emergency procedures if the tank began to sink, approximately 450 Valentine DDs were built primarily for training. About 2,000 Sherman DDs were converted in Britain. About 300 were converted in the United States. This was a massive commitment of resources. Everything depended on Nicholas Straussler being right. That his canvas curtain would hold, that the tanks would float, that they would reach the beach. If it worked, it would save thousands of lives. If it failed, it would be a disaster. June 6th, 1944. D-Day. The largest amphibious invasion in history. In the early hours of the morning, Allied transport ships positioned themselves off the beaches of Normandy. Inside, DD tank crews prepared. They checked seals. They tested inflation systems. Some prayed. Everyone knew they were pioneers. Tanks had never been used this way in real combat. The plan was to drop the DD tanks approximately 2 miles, 3 kilometers offshore. They would swim to the beach, arrive before or with the first wave of infantry, and provide critical suppressive fire. But sea conditions were marginal. Waves were 4 to 6 feet, right at the safety limit for DD tanks. Some commanders hesitated. Were the conditions suitable? Should they risk it? At Utah Beach, the American commander made a critical decision. The waves were too high, too risky. He ordered ships to approach the beach and launched DD tanks into shallower, calmer waters. All DD tanks reached the beach safely. At Omaha Beach, the story was very different. Commanders decided to launch DD tanks at the planned range, approximately 2 miles offshore. Sea conditions were rough. Waves submerged the curtains. Of the 29 DD tanks launched by the 741st Tank Battalion, 27 sank. Only 2 reached the beach. Dozens of crew members died, drowning inside sunken tanks or swimming in the frigid waters of the English Channel under German fire. It was a disaster, but it wasn't Straussler's design fault. It was a tactical decision to launch in unsuitable conditions. The tanks weren't designed to operate in 6-foot waves. At Gold Beach, British, conditions were better. Of the 34 DD tanks launched, 33 reached the beach successfully. They provided vital suppressive fire and helped British infantry advance from the beaches. At Juno Beach, Canadian, 29 of 29 DD tanks reached the beach. Complete success. At Sword Beach, British, 33 of 34 DD tanks reached the beach. Overall, most DD tanks performed as expected. Where they failed, it was due to sea conditions exceeding design limitations or poor tactical decisions. Not a conceptual flaw. Soldiers who landed with DD tank support had a dramatically better chance of surviving the critical first hours. Tanks provided suppressive fire against German bunkers. Soldier morale was higher when they saw tanks alongside them on the beach. Nicholas Straussler wasn't on the beaches of Normandy. He was in England awaiting reports. When they arrived, they were mixed. Success on some beaches, disaster in Omaha, but the overall conclusion was clear. The concept worked. Where conditions were right and tactical decisions were sound, DD tanks were successful. They provided capabilities no other technology could offer. Nicholas had proven his concept in the most difficult arena possible, combat. His canvas curtain had crossed the English Channel. He had helped liberate Europe. The partial success of the DD tanks on D-Day did not end their operational history. DD tanks would be used in multiple subsequent amphibious operations during 1944 and 1945. In August 1944, during Operation Dragoon, the invasion of southern France, DD tanks were used again. Sea conditions in the Mediterranean were generally calmer than in the English Channel. The success rate was high. During the Rhine River crossing in March 1945, DD tanks were used to cross the river under German fire. They performed excellently in a river environment where waves were minimal and distances were short. Nicholas continued refining the DD system during and after the war. He attempted to adapt the system to heavier tanks, the Churchill, the Cromwell, and even the Centurion. He also experimented with the flamethrower-equipped universal carrier, but there was a fundamental limitation. Post-war tanks became progressively heavier. The Churchill weighed 40 tons, the Centurion 50 tons. To float tanks of this mass, the curtain would have to be so high and bulky that it would become impractical. The era of the DD tank was coming to an end, not because the concept was wrong, but because tanks were evolving beyond their applicability. However, the principle Nicholas established, temporary flotation using a collapsible screen, continued to be used in lighter military vehicles. Early versions of the American Bradley fighting vehicle and the British FV-432 used systems derived from the DD concept until the 1980s. Nicholas also worked on other projects after the war. He developed the Lipsoid tire, a very low-pressure, off-road, puncture-proof tire that was used on military and construction vehicles. He worked on several automotive projects, many of which were connected in some way to amphibious vehicles. In the 1950s, Nicholas presented an extremely radical design for a main battle tank. It used a highly flexible suspension he had patented in 1935, combined with canvas for amphibious capability. The design was so unconventional that it never made it beyond the official documents, but it demonstrated that even in his old age, Nicholas still thought radically. Nicholas Straussler died on June 3, 1966, at the age of 75. His obituary in the Times of London recognized his contributions to military vehicle development, particularly the DD system. But to most, his name was unknown. Today, few people know Nicholas Straussler, but anyone who visits tank museums can see his legacy. The Tank Museum in Bovington, England, has a Sherman DD in working condition with intact canvas flotation screens. It's a physical testament to the fact that Nicholas's crazy idea worked. The wreckage of 8 Valentine DDs lost during training rests in Scotland's Moray Firth. 2 are located and regularly visited by recreational, diverse underwater monuments to the revolutionary. Concept: Although Nicholas is primarily remembered for the DD system, his career included many other innovative designs that deserve recognition. During the 1930s, Nicholas designed several armored cars for Alvis, the AC-1, AC-2, and AC-3. These vehicles featured four-wheel drive and advanced independent suspension systems, unusual features for the time. The AC-2 was particularly interesting. Nicholas designed it while simultaneously working for British and Hungarian companies. Two prototypes were built. One remained in Hungary for testing. The other was driven across Europe to England, an impressive demonstration journey that also included a presentation to the German military delegation in Nauheim. Although the AC-2 was never adopted by the British Army, its design influenced the development of the 39M Csaba, a Hungarian armored car that saw extensive service during World War II. Ironically, since Hungary was an ally of the Axis powers, Csabas were also used by the German army. Nicholas's design fought for both sides. Nicholas also worked on the Ghana Straussler G3, a four-wheel drive off-road truck used in small numbers by the Germans as an artillery tractor. This vehicle had the unusual feature of being powered by two coupled engines, Nicholas's unconventional solution to the power problem. In Hungary, Nicholas designed the V4 amphibious tank, also known as the light tank V4, in the 1930s. It used a unique suspension system developed by Nicholas and a dual-drive design, meaning it could be driven with or without tracks. The concept was popular in the 1930s, although it proved impractical. The V4 prototype suffered mechanical problems and limited off-road capability. The Hungarian army chose the Toldi, based on the Swedish Landsverk L60, instead. But the V4 demonstrated Nicholas's innovative thinking. He was willing to try radical concepts even if they eventually failed. One of Nicholas's most successful designs was the Alvis Straussler bomb trolley. Approximately 10,000 were manufactured for the Royal Air Force to transport bombs, primarily within airfields. Each carried 4 250-pound bombs. It was a simple, practical device, a rarity for Nicholas that saw widespread use. Nicholas also worked on the Straussler conversion and experimental modification of the QF 17-pounder and QF 32-pounder anti-tank guns. The guns were equipped with motorized carriages. Modified ammunition limbers would be attached to the gun's trails, effectively creating a four-wheeled, self-propelled vehicle and eliminating the need for a truck to tow the gun. The idea of equipping large artillery pieces with engines to give them a limited amount of independent mobility would eventually be adopted post-war with guns like the FH-70. Nicholas was decades ahead of the curve. The pattern throughout Nicholas's career was clear. He was an outside-the-box thinker, willing to try unconventional solutions. Many failed. Some worked brilliantly, but all were interesting. Nicholas Straussler's story offers valuable lessons about innovation, engineering, and unconventional thinking. First lesson: crazy ideas are not impossible. When Nicholas proposed floating 30-ton tanks using canvas curtains, the reaction was skeptical. Fabric against water? Canvas supporting tanks? It seemed absurd, but Nicholas understood the physics. Volume displaces water. Displaced water creates buoyancy. The material creating the volume, metal, wood, or canvas, is irrelevant as long as it is waterproof and structurally sound. Many truly innovative ideas seem crazy at first, not because they violate the laws of physics, but because they violate psychological expectations. We're accustomed to certain materials for certain applications. Breaking those associations feels wrong, even when technically sound. Lesson 2. Test aggressively. Nicholas didn't argue theoretically. He built prototypes. He tested them in lakes. He sank tanks. He learned from failures. He improved designs. He tested again. This iterative cycle of test, fail, improve is essential for true innovation. Many engineers stop at the design stage. Nicholas built hardware. When the Valentine DD prototype sank in 1942, it could have been the end of the project. Instead, it was a learning opportunity. What went wrong? Why? How to fix it? This mindset turned setbacks into progress. Third lesson: simplicity is not a lack of sophistication. Nicholas often created overly complex designs. His suspension systems were ingenious but difficult to maintain. His mechanical solutions were elegant but impractical. But the DD system was relatively simple: canvas, rubber tubing, compressed air, track-driven propellers. It wasn't elegant. It was functional. Sometimes the best designs are those that do just enough to solve the problem, no more. Nicholas learned this late in his career, but he applied it well in DD Lesson 4. Timing matters as much as technology. Nicholas had been working on floating since the 1920s, but it wasn't until 1940-44, when the need for amphibious invasions became critical, that his technology found a receptive audience. The same technology presented in 1935 would have been rejected. No immediate need, no funding, no military interest. But in 1941, with the invasion of Europe on the horizon, amphibious tanks became a priority. Innovators need not just good ideas, but the right timing. Fifth lesson: legacy is not fame. Nicholas Straussler never became a household name. No Hollywood films, no popular biographies, very little public recognition. But his work saved lives. DD tanks reached the beaches. They provided suppressive fire. They helped soldiers survive. Thousands lived because Nicholas solved the problem of making tanks float. That's real legacy. Not personal recognition, but lasting impact. Nicholas would probably prefer it that way. He was an engineer, not a celebrity. Lesson 6: persistence overcomes skepticism. From the 1920s until 1941, Nicholas worked on flotation. 2 decades of experimentation before significant success. How many people would give up after 5 years? 10 years? 15? Nicholas didn't give up. He believed in the solution. He continued refining, testing, and improving. Eventually, persistence overcame skepticism. This is a characteristic of true innovators. They believe when no one else does, and they work until they're proven right. Today, 79 years after D-Day, the name Nicholas Straussler is unknown to most people. There are no public monuments, no Hollywood films, no best-selling biographies, but his legacy lives on in subtle places. In tank museums around the world, Sherman DDs are on display. Visitors look at folded canvas curtains and often wonder. It seems so simple, so improvised. How could it possibly work? But it worked. And that's the glory of Nicholas's design. It was so simple that it seems obvious in retrospect. Great inventions often seem obvious after the fact. No one said it's obvious until Nicholas proved it. At the Tank Museum in Bovington, England, there's a Sherman DD in working condition. Occasionally, during special events, the curtain is inflated. Spectators watch as a screen rises around the tank. In minutes, the metal tank transforms into a boat. Children laugh. Adults take pictures. Few know the name of the man who invented it, but everyone understands its genius, doing the impossible with simple means. In Normandy, France, a Sherman DD is preserved on Gold Beach. Tourists pose next to it. Many don't know that this tank floated 2 miles across the English Channel under German fire on June 6, 1944. At the bottom of the Moray Firth in Scotland, 8 Valentine DDs lie where they sank during training. Divers visit them regularly. They are war graves. Crew members died in these tanks, training for operations they would never perform. But their sacrifice helped perfect techniques that saved others. These wrecks are physical monuments to Nicholas's concept. They demonstrate both risk and promise. Amphibious tanks were dangerous, but they were also revolutionary. Hungary, Nicholas's home country, has a complicated relationship with his legacy. Nicholas left before World War I. He became British and worked for the British Army. But he also sold designs to Hungarian companies. During World War II, vehicles based on Nicholas designs fought for both sides. 39 Mem Saba served Axis forces. Sherman Dedes served the Allies. Nicholas was literally fighting against himself. After the war, Communist Hungary did not celebrate émigrés who worked for the West. Thus, Nicholas was forgotten. Only recently have Hungarian military historians begun to recognize his contributions. In the UK, Nicholas is remembered in specialized circles, tank historians, military enthusiasts, and engineers studying amphibious vehicles. But among the general public? Unknown. There are reasons for this. Nicholas didn't promote himself. He didn't seek publicity. He was an engineer, not a showman. He preferred designing solutions to writing memoirs. Furthermore, weapon systems don't have heroes the way battles do. We know the names of generals who won battles. But how many of us know the names of engineers who designed weapons that won wars? However, a study of military history reveals the truth. Technology often matters as much as strategy. And the engineers who create this technology deserve recognition. Nicholas Straussler never received significant military honors. No medals, no decorations. He was a civilian, a contractor. Not a war hero by traditional standards, but in a real sense, he was a hero. His canvas curtain crossed the beaches of Normandy. His DD system provided tactical advantage when it mattered most. His unconventional solutions solved problems that conventional engineers declared insoluble. If there's any justice in history, Nicholas Straussler should be remembered, not just by experts, but by all who value innovation, intellectual courage, and a willingness to think differently. This documentary is our attempt to begin that correction. Nicholas Straussler deserves to be known. End. This is an educational documentary about the history of technology and biography. The content deals with weapons development in a purely historical and educational context. In 1916, as soldiers died by the thousands in the trenches of World War I, an American mechanic had an idea that the generals considered insane, transforming a hunting rifle into an automatic combat weapon. The military laughed at him. The experts said it was impossible. But John Browning was about to create the most lethal weapon of the 20th century, a machine gun that would forever change the way wars were fought. This is the story of the man who dared to challenge the impossible. John Moses Browning was born in 1855 in Ogden, Utah, into a family steeped in gunpowder and metal. His father, Jonathan Browning, was a pioneer gunsmith who made rifles for settlers and hunters in the American West. The family workshop was attached to the house, and the smell of gun oil and metal sawdust was a part of John's childhood. At 7 years old, while other children played in the streets, John was already at the workshop bench, watching his father's every move. He saw how metal bent under the heat, how parts fit together with millimeter precision, how a simple mechanism could unleash a controlled explosive force. To him, weapons weren't instruments of death, they were mechanical puzzles waiting to be solved. At 13, John built his first complete rifle using only scrap metal found in the workshop. It wasn't just functional, it was superior to many commercial rifles of the time. His father recognized immediately. This boy had extraordinary talent. It wasn't just manual skill. John could visualize complex mechanisms in his mind, understand how forces were distributed through gears and springs, and predict how different parts would interact under pressure. The Browning family was Mormon, and their religion profoundly shaped John's character. He grew up with values of hard work, persistence, and the belief that God gave people talents to be used for the benefit of humanity. John believed his gift for mechanics had a higher purpose. When he was 19, his father died suddenly. John took over the family workshop with his brothers, but it soon became clear that he wasn't just a gunsmith, he was a natural inventor. While other gunsmiths copied existing designs, John began to completely reimagine how guns worked. In 1879, he patented his first single-action rifle. It was revolutionary, simpler, more reliable, and more accurate than anything else on the market. The Winchester Repeating Arms Company, one of America's largest firearms manufacturers, immediately purchased the patent. It was the beginning of a partnership that would last decades. Over the next few years, John created an impressive series of innovations. He developed repeating rifles, pump-action shotguns, and semi-automatic pistols. Each project broke technical barriers that other engineers considered impossible. European manufacturers studied his designs with envy. Hunters and professional shooters competed for his weapons. But John had a particular obsession, creating a truly automatic weapon. A weapon that could fire continuously as long as the trigger was held down. This idea fascinated him, not because of a thirst for destruction, but because of the sheer technical challenge. How to harness the energy of a shot to eject the empty cartridge, load a new one and fire again. How to control recoil. How to prevent the weapon from overheating or jamming. The military at the time wasn't interested. Automatic weapons existed, like the Maxim machine gun, but they were huge, heavy, complex, and incredibly expensive. No one believed an automatic weapon could be practical for battlefield use. John Browning was about to prove everyone wrong. It was an ordinary summer day in 1890. John Browning was at a shooting range, testing one of his new rifles. Each shot produced a cloud of hot gases that escaped from the barrel after the bullet was expelled. John observed these gases with scientific attention, as he always did. For him, each shot was an experiment in applied physics. Then something happened that would change the history of firearms forever. As he fired close to the ground, John noticed the exhaust fumes moving the grass around the rifle. The vegetation bent violently with the invisible force of the gases. It was a phenomenon every shooter had seen thousands of times, but no one had truly observed with the eyes of an inventor. John stood frozen, watching. His mind began to race. Those gases had power, wasted power, power that was simply released into the air with each shot. What if that energy could be captured? What if it could be redirected to operate the gun's own mechanism? He rushed back to his workshop with an excitement his brothers recognized immediately. When John had that gleam in his eye, it meant he'd envisioned something revolutionary. For weeks, he worked on sketches and calculations. He needed to create a system that would channel the gases from the shot to move a piston. This piston would eject the empty cartridge, load a new one from the ammunition belt, and prepare the gun for the next shot, all automatically. It was brilliantly simple in theory, but incredibly complex in execution. The pressures involved were enormous. The timing had to be perfect. If the mechanism opened too early, gases would escape and there wouldn't be enough force. Too late, and the pressure would damage the parts. The gas temperature was another problem. Overheated metal expanded and changed its properties. John began building prototypes. The first exploded on the test bench. The second jammed after 3 shots. The third worked for 20 shots before breaking a spring. Each failure taught him something. John didn't see failures. He saw data. He adjusted dimensions by fractions of a millimeter, tested different metals, and modified spring angles and tensions. His brothers sometimes questioned whether all the effort was worth it. After all, Winchester already bought all his conventional rifle designs. They were making money. Why risk it all on a crazy automatic weapon idea that no one was asking for? But John was driven by something beyond profit. It was the sheer need to solve the problem. It was the certainty that it was possible, even when everyone else said it wasn't. It was the vision of seeing that grass moving with the gases and knowing he had discovered a fundamental principle no one else had grasped. After months of obsessive work, he finally had a working prototype. It was a gas-operated machine gun capable of continuous fire. He tested it in secret, firing hundreds of rounds without stopping. The weapon heated up but didn't break. The mechanism worked like a Swiss watch, even under extreme stress. John knew he had created something special, but he didn't yet know that that moment of watching the grass move would result in the most influential weapon in modern military history. In 1891, John Browning presented his new automatic machine gun to the United States Army. He was confident. The weapon was technically superior to anything else. It was simpler than the Maxim, more reliable and lighter. He had solved problems that other engineers considered impossible. The demonstration was held at a military base in the presence of high-ranking officers. John carefully prepared the weapon, loaded the ammunition belt, and began the test. The machine gun roared, firing with impressive accuracy and consistency. Empty cartridges flew through the air. The target at the other end of the field was completely destroyed within seconds. When silence returned, John expected applause. Instead, he found skeptical looks and expressions of disinterest. One general commented that the weapon was interesting as a technical curiosity, but had no practical application. Another said that machine guns were defensive equipment for fortresses, not field weapons. A third officer simply said that the army already had Maxim machine guns and saw no need to replace them. John was perplexed. He tried to explain the advantages. Its design was simpler, with fewer moving parts, meaning less chance of failure. It was lighter, making it easier to move around the battlefield. The gas-operated system was more efficient than the Maxim's recoil system. Every technical argument was met with polite disinterest. The truth was that the military of 1891 still thought in terms of 19th-century tactics. Battles were decided by infantry, marching in formations, firing in coordinated volleys. Machine guns were seen as specialized equipment for defending fixed positions. The idea that automatic weapons could completely revolutionize warfare had not yet penetrated the conservative military mindset. John returned to Ogden frustrated, but not defeated. He knew his invention was revolutionary. If the American military couldn't see it, perhaps he needed a different approach. He began demonstrating the weapon to private manufacturers and foreign military officials. Some expressed interest, but none were willing to invest in mass production. For years, John continued perfecting the design while working on other projects to pay the bills. He created the famous Colt M1911 pistol, which would become the standard sidearm of the U.S. Army for 70 years. He developed new shotguns and rifles, but the automatic machine gun remained his unrequited passion. What John couldn't have foreseen was that the world was about to change dramatically. In Europe, political tensions were rising. Rival empires were amassing weapons and forming dangerous alliances. Nationalism was inflaming populations. Territorial disputes were creating flashpoints across the continent. It was a pressure cooker waiting to explode. In 1914, the assassination of an Austro-Hungarian archduke in Sarajevo lit the fuse. Within weeks, all the major European powers were at war. World War I had begun, and with it came a form of conflict no one had anticipated: trench warfare. Millions of men dug holes in the earth and faced each other across open fields covered in barbed wire. In this new and terrifying kind of warfare, machine guns suddenly became the most important weapons on the battlefield. And John Browning had just what the world needed. The trenches of World War I created a type of combat no one had imagined. On one side, soldiers took shelter in deep ditches, protected by barbed wire and sandbags. On the other side, just a few hundred meters away, enemies did the same. Between them stretched no man's land, an open field of mud, craters, and death. Traditional military tactics collapsed in the face of this reality. Generals ordered attacks in which thousands of soldiers would leave their trenches and rush toward enemy lines. It was organized suicide. Machine guns positioned in the enemy trenches massacred the attackers before they could get close. In a single day of the Battle of the Somme, the British Army lost 60,000 men, most of them killed by machine gun fire. Machine guns available at the time, particularly the German Maxim model, were extremely effective for defense. But they had critical limitations. They were heavy, requiring teams of 4 to 6 men to transport them. They were mounted on fixed tripods. They overheated quickly, requiring complex water cooling systems. They were composed of hundreds of delicate parts that often jammed in the mud of the trenches. The American army watched the European war with growing concern. When the United States entered the conflict in 1917, it became clear that they would need machine guns, many of them quickly. American forces were drastically under-equipped. There were only a few hundred Maxim machine guns available, woefully insufficient to equip an army growing to millions of soldiers. It was then that military officials remembered a certain Utah inventor who had demonstrated a machine gun years earlier. John Browning, now 62, was summoned to Washington. This time, the generals weren't skeptical, they were desperate. The news from the trenches was horrific. They needed superior weapons, and they needed them now. John introduced not one, but 2 machine guns. The first was an improved version of his original gas-operated design. The second was something even more innovative, a water-cooled heavy machine gun based on a completely different principle. Instead of using gases to operate the mechanism, it used the recoil of the shot itself. Each time the weapon fired, the barrel recoiled slightly, and this movement activated the reloading mechanism. The demonstrations were spectacular. Browning's heavy machine gun fired continuously for several minutes without jamming. It was simpler than the Maxim. It had only 40 major moving parts, compared to the Maxim's 200. It could be manufactured more quickly and was more reliable in adverse conditions. The officers present were impressed, but there was a critical problem: time. Building factories, training workers, producing specialized tools, establishing supply chains. All of this would take months. American soldiers were being sent to France and dying with inadequate weapons. Every week of delay meant more lives lost. John Browning, at what many would consider retirement age, embarked on the most intense project of his life. He worked 18 hours a day, supervising production, troubleshooting manufacturing problems, and training military gunsmiths. His machine gun needed to function perfectly, and it needed to be in the hands of soldiers as quickly as possible. The race against time had begun. The most fascinating aspect of Browning's design was its unlikely origins. While most military engineers began with wartime requirements and created weapons from scratch, John had taken the opposite approach. His fundamental principles came from observing hunting. Instruments designed for accuracy and reliability in harsh natural conditions. John had spent decades designing rifles and shotguns for hunters. These weapons needed to function flawlessly in the extreme cold of the mountains, the humidity of the forests, and the dust of the deserts. A hunter depended entirely on his weapon. One failure could mean weeks of lost supplies. This demand for absolute reliability shaped Browning's design philosophy. When he observed the gases moving the grass that day in 1890, he was testing a hunting rifle. The revelation that wasted energy could be captured and reused came not from a sophisticated military laboratory, but from a rural shooting range. It was the kind of innovation that could only come from someone who truly understood weapons at a fundamental level, not just as instruments of war, but as precision machines. The gas-operated system John developed was elegantly simple. A small hole in the barrel allowed a portion of the firing gases to be diverted into a cylinder. These gases pushed a piston, which in turn moved the bolt. The bolt ejected the empty cartridge, compressed a return spring, and was then pushed back by the spring, loading a new cartridge from the magazine. The entire cycle occurred in fractions of a second. But simplicity doesn't mean ease. Every component had to be designed with micrometer precision. The amount of gas diverted had to be precise, too little, and the mechanism wouldn't have enough power. Too much, and the parts would suffer excessive wear. The timing had to be perfect to prevent the bolt from opening, while dangerous pressure still existed in the barrel. The materials had to withstand extremely high temperatures and repeated impacts. John tested dozens of different configurations. He experimented with different gas port diameters, different piston lengths, and different spring tensions. Each variation was tested to destruction, firing thousands of rounds until something broke. Then he analyzed the flaw, identified the weakness, and designed a solution. What emerged from these years of development was a weapon that incorporated surprisingly advanced design principles. The system was self-regulating. If the gas pressure was too high, the piston moved faster, but the recoil mechanism absorbed the excess energy. If the pressure was too low, the system still operated just slightly slower. This tolerance for variation made the weapon reliable even with inferior ammunition or in extreme environmental conditions. Another brilliant aspect was its ease of maintenance. The weapon could be completely disassembled in minutes without special tools. Parts could be replaced in the field. Ordinary soldiers could perform basic repairs. This was revolutionary. Previous machine guns required specialized gunsmiths for any maintenance. John had transformed hunting weapon principles into a weapon of war. But the ultimate test remained. Would it work in the hellish conditions of the European trenches? When the U.S. Army approved Browning's machine guns in 1917, an impressive engineering feat had to be matched by a miracle of industrial production. Manufacturing tens of thousands of complex weapons in a matter of months was a challenge that would test the limits of American industry. The M1917 heavy machine gun, based on Browning's recoil loading design, was the top priority. It had 40 major parts that needed to be manufactured to extremely precise tolerances. Each component had to fit perfectly with the others. Variations of even 1/10 of a millimeter could mean the difference between a perfectly functioning weapon and one that fatally jammed. The U.S. government mobilized industry on an unprecedented scale. Automobile factories were converted to weapons production. Machine tool companies created new, specialized equipment. Metallurgical companies developed special alloys that could withstand the extreme stresses of continuous fire. It was a national effort. John Browning was at the center of it all. He constantly traveled between factories, solving production problems. When workers had difficulty manufacturing a specific part, John redesigned the component to make it easier to manufacture without compromising function. When questions arose about materials, he suggested alternatives. When testers reported problems, he identified solutions immediately. One of the biggest challenges was standardization. Unlike commercial products, where each unit could be slightly different, military weapons required complete interchangeability. A part from a machine gun manufactured in Ohio had to work perfectly in a weapon manufactured in Connecticut. This required rigorous quality control and extremely consistent manufacturing processes. The Colt patent firearms manufacturing company led the production of the M1917. Workers worked 3 shifts, 24 hours a day. Women entered the workforce en masse, operating complex machines and performing quality inspections. Many became highly skilled operators, manufacturing parts with precision equal to or greater than that of the men they had trained for years. Each machine gun was extensively tested before being shipped. Batteries of tests included firing thousands of rounds under various conditions. Weapons were exposed to mud, sand, water, and extreme temperatures. Those that failed were completely disassembled, and the problems were identified and fed back into the manufacturing process. It was a continuous cycle of improvement. Production of the lighter version, the Browning automatic machine gun, BAR, also accelerated. This weapon was particularly innovative. It was light enough to be carried and operated by a single soldier, yet packed automatic firepower. It was essentially the first modern assault weapon, though that term didn't yet exist. Within months, American factories were producing hundreds of machine guns a day. Special trains transported the weapons to ports, where they were loaded onto ships bound for France. Each wooden crate contained a weapon that represented thousands of hours of engineering, hundreds of hours of manufacturing, and the hope that it would be the difference between victory and defeat. But the real test would come on the battlefields of Europe, where desperate soldiers waited for any advantage against an entrenched and relentless enemy. The first M1917 machine guns arrived in France in early 1918. American soldiers, many seeing combat for the first time, received rapid training in the new weapons. Instructors emphasized the simplicity of Browning's design, showing how to disassemble, clean, and reassemble the weapon took only minutes. Soldiers were impressed by how intuitive the mechanism was. The baptism of fire came during the German Spring Offensive of 1918. German forces, aware that fresh American troops were arriving in large numbers, launched a massive attack, attempting to win before the balance of power shifted irrevocably. Thousands of German soldiers advanced across no man's land in dense waves. M1917 machine guns opened fire for the first time in real combat. The sound was different from that of German Maxim guns, a deeper, more constant roar. The rate of fire was 400 to 600 rounds per minute, creating a barrage of bullets that devastated anything in front of them. American soldiers watched in amazement as the guns fired continuously without jamming. What truly set the M1917 apart was its reliability under extreme conditions. Trenches were a terrible environment for any machine. Constant mud, humidity, fluctuating temperatures, and dust and dirt getting into every mechanism. Maxim machine guns frequently jammed in these conditions, requiring constant cleaning and careful maintenance. The M1917 kept working. Field reports began to reach commanders. One machine gun had fired 20,000 rounds in a single day of battle, with only a short pause to replace its overheated barrel. Another had been partially buried by an artillery shell, dug out, quickly cleaned, and returned to service within minutes. Weapons that had fallen into mud puddles were shaken out, had their basic mechanisms cleaned, and continued operating. The bar, the lighter version, proved equally revolutionary. Soldiers could advance while carrying automatic fire with them, rather than relying on fixed machine guns in the trenches. This fundamentally changed infantry tactics. Assault teams used the bar to suppress enemy positions while other soldiers advanced. It was a completely new concept in mobile combat. The Germans quickly realized they were facing something different. Their intelligence reports mentioned new American machine guns of exceptional reliability. Captured German soldiers reported that their own MG-08 machine guns, while excellent, were more difficult to maintain in field conditions. Browning's weapons had a clear technical advantage. It wasn't just the technical specifications that mattered. It was the psychological effect. Soldiers carrying M1917s or bars felt more confident. They knew their weapons would work when they needed them. This confidence translated into better combat performance. Commanders could plan tactics knowing that automatic firepower would be reliably available. In September 1918, during the Meuse-Argonne offensive, Browning machine guns were present in force. They played a crucial role in breaking through the German defensive lines. The constant sound of hundreds of M1917s firing simultaneously created a deafening roar that dominated the battlefield. By the time the armistice was signed in November 1918, Browning's machine guns had proven their worth beyond doubt. But their story was only just beginning. The end of World War I in 1918 did not diminish the importance of Browning's machine guns. On the contrary, it solidified them as the world standard. Armies around the globe studied American weapons with envy and admiration. John Browning's design had set new standards for excellence in automatic weapons. The M1917 became the standard heavy machine gun of the United States Army, a position it would hold for decades. It was redesignated the M1917A1 with minor improvements based on field experience. Air-cooled versions were developed for situations where a water system was impractical. Each iteration maintained the fundamental principles of Browning's original design. The bar had an equally impressive fate. It was adopted by military forces in over 20 countries. Modified versions were used as hunting weapons and by law enforcement agencies. During the Prohibition era in the United States, both police officers and gangsters used bars. Their automatic firepower made them infamous in urban shootouts. John Browning continued, working even after his triumph in World War I. He was now in his early 60s, an age when many men would consider retirement, but his creative mind was far from at rest. He developed new pistols, innovative hunting rifles, and continued improvements to his existing machine guns. In 1921, he was in Herstal, Belgium, working with arms manufacturer FN Herstal on a new pistol design. It was a normal day at work in the workshop when John experienced chest pains. He tried to keep working. After all, it was what he had done all his life. But the heart attack was devastating. John Moses Browning died at his workbench, surrounded by the tools and projects he loved. He was 66 years old. His death was reported in newspapers around the world. Obituaries described him as the greatest weapons inventor who ever lived. Military personnel from several countries paid tribute. But the true tribute to John would come in the following decades, when his inventions would continue to shape global conflicts. During the years between the world wars, Browning's machine guns were continually refined. Military engineers made minor adjustments based on years of use. Materials were improved with advances in metallurgy. Manufacturing processes became more efficient. But the core design remained essentially the same as John had created. The M2, a larger 50 caliber version of Browning's heavy machine gun, was developed in 1933. This weapon would be perhaps his most enduring legacy. Capable of penetrating light armor and downing aircraft, the M2 combined devastating power with the reliability characteristic of Browning designs. It was such a well-designed weapon that it would remain in active military service for over 90 years, an absolutely remarkable record. As war clouds began to gather again over Europe in the 1930s, armies around the world prepared frantically. And in arsenals across dozens of countries, Browning machine guns were being pulled from storage, cleaned, tested, and readied for another global conflict. The Utah mechanic, dead for years, was about to influence another world war. When World War II broke out in 1939, the Metral Browning machine guns were present in virtually every theater of operation. The M19-9, a lighter, more portable version of the M1917, equipped vehicles, aircraft, and infantry positions. The 50 caliber M2 became ubiquitous, mounted on tanks, jeeps, ships, planes, and fortifications. World War II was fundamentally different from World War I. Instead of static trench warfare, it was a war of rapid movement, tanks cutting through fields, aircraft dominating the skies, Marines assaulting Pacific beaches. Browning's machine guns needed to function in each of these extremely diverse environments. In the North African desert, fine sand penetrated every mechanism. German MG-34 and MG-42 machine guns, though excellent in many respects, suffered from frequent jams. The Brownings continued to function. British and American soldiers developed an almost religious respect for the weapon's reliability. Tank commanders particularly loved the M2. It could fire at enemy aircraft, suppress fortified positions, and penetrate lightly armored vehicles. In the jungles of the Pacific, the war against Japan presented unique challenges. Extreme heat, constant humidity, dense vegetation, and close-quarters combat. American Marines relied on the bar as a squad weapon. In fierce battles on islands like Guadalcanal, Iwo Jima, and Okinawa, the bar's sustained automatic fire often made the difference between capturing a position and being repulsed. American bomber aviators relied entirely on Browning 50 caliber machine guns for defense. B-17 Flying Fortresses carried up to 13 M2 machine guns. When formations of German fighters attacked, the sky filled with red traces. Gunners in turrets swung their guns in complex arcs, firing thousands of rounds per mission. Reliability was literally a matter of life and death. A jammed gun could mean a defenseless bomber. Production during World War II reached impressive levels. American factories produced more than 2 million Browning machine guns in various calibers. Women once again made up a large portion of the workforce, operating precision machinery and performing complex assembly work. The industrial infrastructure created during World War I expanded dramatically. After 1945, while other weapons were retired or replaced by more modern designs, Browning machine guns remained in service. In the Korean War of the 1950s, soldiers used the same M19 919s that had equipped their fathers in World War II. In Vietnam in the 1960s and 1970s, the M2 remained the primary heavy machine gun, now equipping helicopters in addition to ground vehicles. What was remarkable was not just longevity, but continued performance. Military engineers repeatedly attempted to develop replacements for the Browning machine guns. Prototypes were tested, contracts were awarded, new designs were officially adopted. But time and again, soldiers in the field preferred the old, reliable Brownings. The M2 in particular defied all replacement efforts. In the Middle East wars of the 1990s and 2000s, more than 80 years after John Browning observed gas-moving grass, their machine guns were still in active combat. Soldiers in Afghanistan and Iraq mounted M2s on Humvees and at forward bases. The weapon that had faced German planes over Europe now faced insurgents in the desert. The story of John Moses Browning transcends the biography of a simple inventor. It is the story of how an individual with exceptional talent and relentless determination could literally change the course of world history. The weapons he created influenced conflicts that shaped the 20th century and remain relevant in the 21st century. The .50 caliber M2 remains in active service in over 100 countries. No other firearm in history has a comparable service record. From its adoption in 1933 to the present, it has spent over 90 years in continuous military use. Modern engineers with sophisticated computers, advanced materials, and decades of additional experience have been unable to create something fundamentally superior to the design John created with paper, pencil, and brilliant mechanical intuition. The gas-operated principle John discovered by observing moving grass became the basis for most modern automatic weapons. Assault rifles like the American M16, the Russian AK-47, and countless others use variations of the system John developed. He didn't just invent specific weapons. He discovered fundamental principles that defined an entire category of technology. But beyond the technical specifications and service records, there's something deeper to Browning's story. It's about the nature of genuine innovation. John had no formal engineering education. He never attended university. He didn't have access to sophisticated laboratories or research teams. What he did have was careful observation, creative thinking, and a willingness to test ideas repeatedly until they worked perfectly. His design philosophy was elegant. Create mechanisms with as few moving parts as possible. Use natural forces instead of fighting them. Build tolerances into systems so they continue to function even when individual components wear out. These principles seem obvious in retrospect, but they were revolutionary in their time. John registered 128 patents during his lifetime. In addition to machine guns, he created pistols, rifles, shotguns, and even automatic cannons. Many of his designs continue to be manufactured and sold commercially more than a century later. The Browning high-power pistol, completed after his death by his apprentice Dieudonné Sève, was adopted by more than 50 national armies. There's a poetic irony to Browning's legacy. He was a fundamentally peaceful, deeply religious man who believed in using his talents for constructive purposes. But his most influential creations were instruments of war. Millions of people were killed by weapons based on his designs. He never publicly expressed conflict about this, but it's hard to imagine he didn't reflect on the consequences of his inventions. Perhaps the best way to understand John Browning is to see him as a pure problem solver. He saw mechanical challenges and couldn't resist solving them. The fact that his solutions were used in war wasn't his primary goal. It was the inevitable consequence of living in an era of global conflict. Had he been born in a different era, perhaps his genius would have been applied to agricultural machinery or industrial tools. The mad mechanic who transformed a hunting rifle into a war legend never considered himself special. To him, it was just work. But his work changed the world in ways he could never have fully anticipated, and more than a century later, his legacy continues to soar.